Alright, good afternoon everyone. Welcome to the 8th lecture in COMP1511, our second lecture in week 4. Alright, so big news in COMP1511, or big news in UNSW, is we're moving teaching pretty much basically back online. It's not quite that simple. So across the university, my understanding is we're pushing teaching back online where we can, because of the COVID outbreak in New South Wales, of course, which is, well, I guess some of you aren't in New South Wales. For those of you who are not in New South Wales, we have a small but COVID outbreak, but it includes at least one member of Parliament, so it's all sorts of news here about that. And it's clustered around the eastern suburbs of New South Wales, eastern suburbs of Sydney, where New South Wales Uni is, of course. So to make life a bit easier, UNSW has decided to move teaching back online while we can. We don't do this lightly. We're trying to get students back to campus, but we'll have to wait. How long will it have to wait? We're going to do it for the rest of this week and next week, so that's week 4 and week 5, the next 9 days, I guess it is 10 days. And then we've got flexibility week where we don't have any classes anyway. So we're hoping, fingers crossed, the COVID outbreak will be gone before week 7, and we'll be back on campus with activities happening. So if you have a face-to-face Tute Lab, hopefully it's back in week 7. But for weeks 5 and 6 it's online, and in your email there's detailed instructions from Tom about how to get to your online class. Don't hesitate to ask in the course forum if there are any problems. Oh, I'm checking my level. My level's a bit loud now. Sorry. Okay, that might not be that much. Oh no, that's too. There we go. All right. So that's what's happening with COVID. Apologies for there's a little bit of there's a lot of confusion around the university as yesterday as we try to work out how to best respond. It takes a while to get an organisation of this size to do things. But a big thank you to Tom and others and the tutors who have moved to try and get everything sort of sorted out there. So I guess, yeah, I said UNSW is moving on, learning online where it won't have a big impact on the learning. Something you might still have some classes coming face to face if they can't easily be done online, depending on what other courses you're taking. But we're well adapted to online, so we're online now. If you do need to come into campus still for other courses, you don't need to come in for COMP1511 now. It's hugely important you don't come into a campus if A, you've got anything resembling a COVID symptom, anything like sore throat, headache, temperature, any of those possible symptoms. It's very important you don't come near campus. What you should be doing, of course, is getting a COVID test. The second thing is, if you have classes on campus, you have to wear a mask. So those are the important things, I think. All right. What else what's happening in COMP1511 otherwise apart from the move online? Assignment 1 came out. A big thank you for Tom in particular, well, with Jenny, of running a live session on Tuesday, late Tuesday. If you look on the lectures page, there is a link if you missed it, but Tom did a huge walkthrough through the assignment, and thank you to the students who followed the live session live and asked questions in the chat, which are probably they were good questions. They're the sort of questions you might have if you've missed it. So by all means, look at the recording and hear Tom's answers.
I'll note that we're probably going to put that up on the assignment 1 page as well, along with some hyperlinks to particular time codes in there as well. That should be happening tonight or tomorrow morning. Just so if you're not sure where to find it, you can look on the lectures page, obviously, but you'll also be able to find it on the assignment specification, just so it's really easy to find.
So if there's a lot of questions coming in about the assignment, say next week, I could probably twist Tom's arm to do another live session, but we'll see. For now, just ask questions in the forum, and that's the best place to let us know what we're happening. Yeah, I guess, how do I get started on the assignment? It's not so easy to tackle an assignment like this. It's our first big program. My biggest piece of advice would be start early, and rather than some people, they sketch out their timetable, that's nice, and they say, in 2 weeks, the assignment's due in 3 weeks time, so in 2.5 weeks time I'll do 20 hours work on these 3 nights or whatever. Don't do that. Please don't do that. you really want to space out the work. You want to start now, work for half an hour, and you'll probably hit some sort of little roadblock, and maybe you'll need to think about it for a day. Maybe you'll need to read the course forum. Maybe you'll need to ask something in the course forum. Maybe you'll need to ask something in your tute. So it's much better if you work for an hour now, get as far as you can, then come back to it tomorrow night or the night after, another hour, and you attack it, start early, and do it in little bursts. By all means, pencil in for the next weekend or something, a big chunk of work, but don't be surprised if you hit a roadblock and can't do your all that work. Yeah.
Worth noting as well that the help sessions are certainly much less busy during the early weeks, and you'll get much more out of them, I would say, if you go to them early and get help there. Also, probably worth noting that all help sessions have now moved online. I think that's only relevant for next week, but help sessions will be online at least until Flexibility Week.
Okay. And it's not just people who have only been coding for a couple of weeks, by the way, that take time. It's a regular thing for me. I'll code away for an hour or two on a problem and not quite solve it and not quite know how to solve it. Then I'll go away and do other things, and maybe standing in the shower the next morning I'll be thinking, I know what to do. I know what data structure I should have done or what I should have created, and I'll come back to the problem and suddenly in 5 or 10 minutes go a lot further with it. You'll find that with assignment 1, I bet. Alright. I would, well, hopefully you can see, assignment 1, it's about an old silly game. Well, it's sort of a very, addictive game. Millions and millions of people have found this a very addictive game, but it's about much more than the game. The skills you're applying and using in this context are applicable in so many contexts. You could be working as a mechanical engineer, having to do a little bit of fluid analysis or understand that. And exactly the same coding patterns would get used for the assignment. The assignment's been particularly chosen. It's chosen to be fun, but it's a really easy place to work on what are complex ideas. So it's easy to see whether you've got the code right or wrong, and learn how to write this sort of code. All right. Assignment 1, weekly tests. So the weekly tests, our first weekly test is due at 8 o'clock tonight. If you haven't done it, you should have got an email, I think. We tried to send out a reminder email, but if you haven't done it, do it after this lecture. Our second weekly test will be out soon, very soon. It's definitely out by tomorrow, and it will be due in a week's time, and that will be the pattern from now on. One weekly test comes in, the next one goes out. Weekly tests, assignment, tutes and labs are happening, of course, and I think that's. Have I covered everything, Tom, that's going on in the course?
That's everything I can think of at the moment. Excellent.
Oh, and a big thank you to who's fielding the chat today. It seems to be Tom, the other Tom. Well, I'd say Tom K. Tom Killingback, but they're both Toms. They're both Tom K. But there we go. So hello to Tom Killingback in the chat. Feel free to ask Tom Killingback questions in the chat. So today's topic, I'm not going to do a recap of what we covered in the last lectures just yet. We will be coming back. So we're racing through this little territory at the moment to get over some key ideas. So you've got a sort of complete foundation of things to work with. But we're going to have to go back and sort of expand our knowledge of arrays and expand our knowledge of even of loops. There's some programming techniques with loops that we need to practice and see a few more examples of. Functions, definitely. There's lots of ways to use functions, and we're just seeing a few simple ones of that. But so don't panic if it seems like there's lots of concepts that we're coming across. Yes, we're racing across a lot of concepts to introduce them. We'll come back and consolidate them, particularly via examples. All right. Now, first, I want to introduce something, and this is not core material. This is not something that we're really trying to teach, but it's helpful. It's just information that's nice to know. Yeah, nice to know. That's the word for this stuff. And the thing that's nice to know I want to talk about is numbers in other bases. So it's helpful to understand what we're seeing if we've got some idea about it. you won't be asked, to write exam questions about this, and there won't be anything that revolves around this, but you'll find it easier to understand some of the things you see if you've got some idea about numbers and other bases. And if you're good at maths, and most of you are pretty good at maths, it comes pretty naturally to you anyway. It's just a sort of a cool thing to see. Alright, so you probably write your numbers in what I'd call decimal or base 10. But what does that really mean? How does that work? You might have got covered in like year 7 or something like that, maybe even before that. But if I write 4705, it's the position of the digit really is very important. The last digit there, the 5, that means 5 times 1. It's in the 10 to the 0 position. The 0 has no effect, but the 7 means a lot more than the 5. That's 7 times 100, or 7 times 10 squared. And the 4 means 4 times 1,000, or 10 cubed. So you can see here, as we write that number, each digit is, I'd say, base 10. Some people use the word radix, but I much prefer base. So it's each digit is base 10, and they refer to successive powers of 10. Now if I keep going, there was another digit, if I add a 3 here to make it 34,000, that would be talking about 3 times 10 to the 4. If I add a 1 there to make that 134,000, that would be talking about 1 times 10 to the 5. So when I say this number here, 4705, is base 10, its whole interpretation revolves around powers of 10. If you want to be precise about this, and who doesn't, you can put that down as a little subscript to say this is a number base 10. Now you say, who would do that? What sort of person would do that? Everyone uses base 10. Well, you're becoming the sort of person who would do that, because you're becoming the sort of person who sees and maybe even writes numbers in other bases. All right, so let me show you using another base. So why do we use base 10? Fingers. So 10 fingers. Let's suppose we only had 7 fingers. What would our numbers look like? So we could instead use 7 cubed, 7 squared, 7 to the 1, 7 to the 0, and so on. So if I write 126 base 7, note my little use of a 7 there to indicate it's base 7, that's actually the same as writing 454 base 10. You can type that into your phone and work it out and check it out. All right, so again, this is just something that's sort of nice to know. Base 7, you may not see again in the rest of your life. I don't know. It doesn't really come up many places at all, except when people like me are doing lectures about bases. But you could write all your numbers in base 7. All right. What about some bases that are really useful? All right. Binary numbers come up a lot in computing because we've talked about it. Underneath, in the hardware, it's all ones and zeros. So if you're going to represent a number, it tends to be binary. So we could write things in base 2. If we write something in base 2, instead of 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, we're talking 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and so on. So if I write 1011 and say it's base 2, what that means is 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, which is the same as writing 11 base 10. By the way, if you want to play with this after, I haven't got a link to it, but if you Google, it's easy to find. People have done little JavaScript apps or things like that that do these conversions, so you can check your knowledge, check a few examples to make sure you got your head around it. Now we won't be asking you to convert. I don't think we'll be asking you to convert to and from binary in COMP1511. We will be in COMP1521. Most of you are going on to COMP1521. Yeah, we'll do exactly that in COMP1521. But it's nice if you've seen this basic idea. If I write it in binary, it's the same as writing it in base 10. All right. One more thing I want to show you. One last thing about bases, because there is a base that is useful. I've said base 7 you'll never see again. If you work with computers, even if you don't work with computers, you'll see it popping up. If a computer breaks, often it prints out some sort of error dump or something like that, which will often contain numbers in base 16. So this is really the point of all of this. I want you to be able to see a number in base 16 and know basically what it means. So base 16. Now, all right, there's one thing I've sort of glossed over, isn't there? What are the digits? What are the digit values? You're saying, what do you mean, what are the digit values? They're 0 to 9. Yeah, that's true. For base 10, you need 10 ways of writing digits, 10 possible digits. They're 0 to 9. If we go to base 7, yeah, well, that's easy. We can just use 0 to 6. So we can just use a subset of the digits we've already got. That's great. Go to base 2. Oh, digits got even easier. They're just 0 and 1. Base 16, we have a problem. We need 16 different digits. We're only used to using 10 of them. We could have invented digits, but yeah, why didn't we invent extra digits? Good question. But it's not something you do in the sort of Anglophone languages, is it? Yeah. So what we've done and said is adopted some letters and said they're honorary digits. They can be digits if they're in a hexadecimal number. And that gives us one way, by the way, to spot hexadecimal numbers. If someone forgets to put a little 16 there and tell you it's a hexadecimal number, if you notice they've used the digit B, that's a pretty big clue. All right. So hexadecimal numbers. 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3, 16 to the 4, 16 to the 5, and so on. So if I write down 3AF1 and say that's base 16, it's 3 times 16 to the 3 plus 10 times 16 squared plus 15 times 16 to the 1 plus 1 times 16 to the 0. And if you do all the little sums there, it'll come out as 1F089. But why, Andrew? Why isn't hexadecimal just a curiosity like base 7? It turns out it's really nice when you're working with computers if you can write out numbers and easily see what their values would be in binary, what bits are what. So but there's a problem with binary. It's just far too many digits. So it makes it hard for humans to read. Numbers would be 1 0 1 1 1 0 1 1 1 0 1 1 1 and 1 1 1 0 1 1 and just keep going. There's far too many digits in binary numbers. Hexadecimal numbers we can write much more compactly. Yeah, well, if I look at that, that's an interesting question. That's a 4-digit hexadecimal number. How many digits would it be as a binary number? And the answer is it's 4 times as many. You'd need 4 binary digits for each of these. So you'd need 16 binary digits. And this, by the way, is handy. There's an easy conversion. You can do this as an exercise and figure it out. But there's a really easy conversion of hexadecimal numbers to binary. So it's easy, given a hexadecimal number, if you to see what a particular binary bit is if you're used to it. I can look at this number and just visualize what it would be as a binary number. See the bottom 8 bits would be 1 1 1 1 0 0 0 1. Now you can't do that. We're not asking you to do that until COMP1521. COMP1521 you will get to do we won't ask you to necessarily visualize it, but you'll see that in COMP1521. So you'll get much more of this in COMP1521, but that's the motivation for it. But for now, what's the message? Just what this means. So if you see a hexadecimal number, you can think, oh, that's how I'd translate it to base 10 and what it means. So this is just all nice to know stuff. Tom has a question from the chat.
Yes. So there was a question about that second dot point there, saying like, why is conversion to decimal awkward and hiding bit value? It might be good just to specifically address
all right.
that point.
So I'll give you the reason. 2 to the 4 equals 16, but actually no, that's, I can write it a better way, can't I? Log 2 of 16 equals 4 exactly. Log 2 of 10 equals, and what does it equals? It's 3 point something 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 something. I can't remember what it is. You can work it out. So because 16 is an exact power of 2, the bits of the digits of a binary number correspond discretely. This is something to go away and play with. But because 10 is not a power of 2, the digits of a decimal number, for example this 9 here and this 8, they don't correspond to separate bits, separate sets of bits. But this F and this 1, when you convert to binary, it relies in there. And again, not part of the topic for this course, very much a topic for Comp 1521, but if this sort of thing engages you and you think it's cool, just go away and play with it a bit and translate it. You could actually, it's well, you've got the assignment to do. I'd say yeah, I wouldn't encourage you to go away and necessarily write program. So if you want to understand this, you go away and write programs about it, and that's exactly what we do in Comp 1521. But it's not what we're going to do. Yeah, no, you probably should work on the assignment instead. All right. So that's it. That's all nice to know stuff. Trying to explain to you, this is a base 16 number, and we're about to write programs that'll print out base 16 numbers, for better or for
Andrew,
worse.
can I just jump in for a moment there? Because I think this is really useful context. But often what I tell my students when we're in the tute is that the main thing to realize is that whenever you see a hexadecimal number, so numbers that have some A's or F's in there as well, and often they start with a 0x, that's just some place in your computer, or it's something to do with binary. And so you can really just think of that like, oh, okay, this is some computery value that's not necessarily supposed to be understood by the human. This is why we use it. Like, it's useful to us because it represents a value for the computer. But if what Andrew's just said doesn't really make sense to you or trying to figure this out, the way you should think about it is whenever you see hexadecimal or whenever you see numbers with letters in it, that's a computer value, a computer address, something like that.
So I would qualify what Tom said there. When you see see a hexadecimal number, you should think it's a value that shouldn't be understood by a human that has not done Comp 1521. In Comp 1521, we'll teach you how to understand what those. You get really well into Comp 1521, and you should understand mostly what those values mean and what sort of values they are. But for now, they're sort of just magic numbers. But yeah, excellent point by Tom, except for the fact he's neglecting all the stuff you're going to learn in Comp 1521. All right, enough with the commercial for Comp 1521. Memory, yeah. All right, I'm going to tell you some things about memory, and there's sort of we're glossing over so much here. That's the nature of university courses. I mean, the great analogy for me is always you learn. Some of you will have done physics in high school, and you learn Newtonian physics, which explains most of the world, but everything you say about Newtonian physics is not exactly true because of relativistic effects. So if you get into Einsteinian physics, there's a second order things, but you don't have to worry about that. You can figure out everything about Newtonian physics and then learn the complications in the world. So we're going to give you an overview, and there are complications which you'll learn about, and not just Comp 15211 in subsequent courses as well beyond that. So let's try and explain this in a way that makes sense to you. How does memory work in our computer? Let's think of the analogy as each piece of memory, we'll say a byte, as being like a house in some gigantic street, we'll say. Well, imagine a neighborhood that's just got one long street. Each house has a unique number which you can find it with. So we'll imagine a town that's just got one long main street and that's it. So how do we find a house on that street? It has a number. It has a unique address, and we'd say we can use that to find it. That might sound familiar already because that's just like an array. What's an array? An array is like a big long street, and you've got a number to pick up the particular element in the array you're talking about. So you can think of what's in your computer as a big array of bytes. And that's actually a pretty good analogy. You have to get a long way into the internals of a computer before it's not simply an array of bytes. That will get you much further than most people go. So you can think of the computer's memory as a big array of bytes. The index into an array, if we're talking about memory, we call that an address, just like a house address. I guess that's where the word, I've never really thought about where the word address comes from in computing, but it probably comes from house addresses. Yeah, good point. Alright, so the address is an integer. Now, I've said it's an integer, but it can be a huge integer, a really big integer. So this lovely little depiction of memory has the addresses as 105, 107, 109. Yeah, that would be nice if we were dealing with addresses like that. If you work with tiny, really tiny computers, the sort of computers, you put in tiny electronic devices or something like this, you might actually deal with addresses that small. But the sort of computer, something like your laptop or a CSE server, the addresses are going to be in the billions probably, rather than the hundreds. Not that it really matters, just that these numbers, when we see them, they'll be much larger. So we put variables in memory. We've said we actually have to use a few bytes generally. If we have the address of the variable in memory, we can find it. And we're going to see how we can use that. Yeah. All right. So analogy is, if we talked about houses, you can think of a variable as a house. That house has a certain location which is in its address. And if I go to the house, I'll find the value, the bits and bytes that hold the current value of the variable. Your laptop, your desktop, CSE servers, most computers these days, most general purpose computers, use 64-bit numbers, 64-bit integers for addresses. You can work out how big that will let you, how big a computer you could build with that. But in practice, we only use a fraction of that address space. Older computers often use 32-bit address spaces. If you can work out how much, if your laptop has 8 gigabytes on it, you can do some figuring. If you had an 8 gigabyte laptop, can you really use the memory if you've only got 32-bit addresses? Yeah, you can. So. And if you went to a tiny little computer embedded inside something, you might see 16-bit addresses or 8-bit addresses. And I've even heard of computers with 4-bit addresses. But 64 is the size of the addresses in all the coding we're going to do in this course. Alright, here's a sort of a summary slide. Reminding of two things. Yeah, an int's 4 bytes on the computers we're going to be using. A double's 8 bytes. So we've got this gigantic array of bytes. So if you have an int variable, somewhere in this gigantic array of bytes are 4 that are set aside for an int variable and 8 for a double variable. This is why I went through all this stuff without bases. Memory addresses usually get printed in hexadecimal. Base 16. They're easier to understand for a couple of reasons than that, and we'll talk about that in COMP1521 with how it's related to how virtual memory works, which we'll discuss in that course and not in this one. Alright, types. I said I wasn't going to recap, but I do want to recap about types. We saw int for whole numbers. We saw double for real numbers, floating point numbers if you prefer. They were the two atomic types, base types, indivisible types we've seen. We've seen arrays now, which are a collection type. You have an array of another type. Array of int, array of double, and in the last lecture we did an exercise with an array of int, a two-dimensional array, and that's what you work with in assignment 1, which is a new world. And there's another sort of meta type that we need to introduce. Not really a collections type, but it builds on other types. The types is pointers. Yeah, this is a simplification, but it's a good way to describe it for now. But don't come back to me in 3 years' time and say this wasn't exactly true, Andrew. There's a complicated world behind here. All right, but you can think of pointers as variables that hold memory addresses. They exist only to point at the location of other variables, so refer to other variables. So a pointer, its job is to lead you off to another variable. If we think of variables as house, a pointer is something that contains the address of the house. Now we've said addresses of variables are integers, so you can think of it as an integer variable that stores a memory address. It's like that. Well, in fact, it's implemented exactly like that on CSE computers, and I can demonstrate this to you. I think I'll switch to coding this up to show you this in progress. All right. So there I've created an int variable. Let me now create a pointer variable. We'll call it IP. And there's one more bit to it. The asterisk. So that asterisk, it's tiny, but makes a gigantic difference. It's an unusual way to write the syntax, but the type of IP is pointer to int. You're saying, well, if it's pointer to int, why don't we put asterisk in? Yeah, interesting question. Do our languages course in 3rd year, and you can get into all the topics here. But fortunately, in COMP1511, we only work with fairly simple combinations of pointers and variables, so that's not too bad. But the big thing is just adding that asterisk. It makes a gigantic difference. This is a variable that holds an int. This is a variable that points at a variable, and the only type of variable it can point at is an int. Yeah, I guess, I forgot to say that, didn't I? So a pointer points at another variable, and a particular pointer variable can only point at one type of variable. Well, I guess I'll show you that. How do I make IP point at that? We have an operator to give us the address of something. It's ampersand. All right. Where have we seen ampersand before? We have. We've been using it all along. without really knowing what it did. And that, of course, it was with scanf. Every time we've done a scanf, we've put an ampersand in front of the variable. Finally, we know what it is. It says, give me a pointer to I. Give me the address of I. And you can call it the address of operator if you like. Right. Well, what now? Well, first things first. Let's peek into what's in IP. There is a special printf format that you don't use in normal programs. If this was a finished normal program, you wouldn't have any %p formats in it. %p is used to peek at the values of pointers. Why would I do that? I would do that if I was debugging. I would do this if I was trying to understand how a program worked. I would do that if I'm sort of doing these meta activities. I don't. If I'm writing code to actually do something, I don't ever need to look at what the value of a pointer is. So it's this extra format which we don't use in normal coding. But to say that, we will use it in. You will use it in debugging. All right. So I think I've got that right. Let's see if we can save it.
Andrew, there's one thing I just want to jump in because there's some talk about it in the chat, just to be super clear about. On line 6, when you're creating IP, the thing that makes it a pointer is that asterisk. So you could name it anything you want. There's no special naming system you have to use for a pointer. We just sometimes use the P at the end to know, oh, this is a pointer. You'll also see some tutors use like _PTR to indicate it's a pointer. But the important thing is that asterisk. The other thing which is super important is that this asterisk is part of the type. IP is the name of the thing, but the asterisk goes with the int. So it's int star. And you'd even hear us say sometimes when we're tutoring, oh, that's an int star as opposed to an int. So just in case anyone there is a little bit confused, what we're introducing here is this new type, this new thing which can a new type of value called a pointer, and we denote it with int star. And you could also say, for instance, double star if you were talking about a pointer to a double.
All right. Yep. So to avoid confusion, I've changed the name of the variable, and the program should still work. Let's look at the value that comes out. All right. There we go. A value's come out. Oh, notice it's printed out with a little 0x there. Because subscripts don't work too well in simple output, in little ASCII output, we don't put a little subscript 16 on to indicate hexadecimal numbers. The C way of doing it is write a 0x before it. If you're in love, actually, no, I shouldn't tell you this, but if you put hexadecimal numbers all through your C program, just putting a 0x before them. Your tutor will then take style marks off you, but you couldn't do that. When you get to later courses where well, it would be a good thing to do, but not in COMP1511. All right. So yeah, Tom's saying often pronounced int star rather than int asterisk to mean pointer to int, and it can't be too emphasized. These are just such different types. They look almost exactly the same, but they're completely different. A world of difference. All right. So that's showing what's in there, and that's actually the address of I in memory. That's the particular byte address where I is stored in memory. So there'll be 4 bytes for I, and that'll be the pointer to. Well, which one is it a pointer to? That's another interesting question, but that leads you to those 4 bytes. Notice it's a gigantic number. And again, that's a topic for COMP1521. Right, what can I do now? There's a few, right. So let me try doing it. Let's create a double variable called D. Let me demonstrate. Tom can't point at a double variable. Actually, all right. I'm gonna go back to calling it p. It's just too. You see, this is what I mean. Don't do things like this. Call your variable hello Tom. It's just too distracting. I've made it going back to p. All right, let's see what DCC says if I try and make p point at the double variable d. I think for line it's going to get to line 9 and say, Andrew, don't do that. That was right. It's it's not. It's saying incompatible pointer types. You've said give me the address of d. D is a double variable, but then you've tried to put it in p, but p can only point at int variables. All right, so let's now try using the pointer variable. Let's see what can I do with p. First, what does that program print? So look at that program. What does it print? Well, it prints out what I. What's you say? It prints out I, but what's in I? Nothing's in I. I's up there, and nothing is assigned to I. So if I run that program, DCC adds extra checking in there to make sure. Oh, if I save my file, run the program, DCC adds x. Oh, it's complaining about D being unused. All right, let me dump D. Just make DCC happy. This time for sure. Oh, in fact, DCC won't even let me compile a programming saying, Andrew, it's saying, Andrew, look, you're printing out I, but you never put anything in it. What are you thinking? That's not allowed. So that's an undefined program, a legal program. We can't do that. All right. So we'll put 456 in there. DCC is saying, oh, you put something. You went to the effort of putting something in P, but never did anything with it. All right, okay. Anything to keep DCC happy. We'll comment at that line this time. Why is my life like this? This time for sure. DCC is happy, and we have a program that prints out 456. All right. If you want to put a hexadecimal in your program, by the way, there's a hexadecimal number in my program, just for the fun of it. Ooh. All right. So that's very much a side note, showing if I put 0x there, I can embed hexadecimal numbers in my program. But we don't want to do that. I don't know why I showed you that. When I could show you something important like this. All right. Anywhere I could use the variable that P points at, I can say asterisk P. So asterisk is the opposite of ampersand in expressions. I guess what would you call it? Dereference. I call it the dereference operator. That says talk about the variable P points at. So the first thing I could do is print out the variable P points at. Let's try that. That says print out the variable P points at. There we go. But I can do other things as well. can assign to the variable p points at. And that will now print out 42. That will print out 42 if I recompile. So that is because p is pointing at I, that's the same as saying I equals 42. Because p is pointing as I, that's the same as saying that, while p is pointing at I. P could be pointing at other int variables. We don't know. And that's really the problem with pointers. It creates this possibility for writing incredibly confusing code. So you've got to be very careful what you do with pointers. Let me show you it a bit different. We'll use p to change I to 24, and then we'll say I equals 37. And now let's see what that program prints out. I encourage you to get little programs like this and run them and see what they print. And do it with DCC on a CSE computer, because DCC checks everything. It's easy with pointers to write little invalid programs and not know you're doing the wrong thing if you're using a regular C implementation. Yeah. So 4 things happened here to I. It got initially created and then given 456 as a value. P was made to point to I. Then we said change whatever variable P points to, happens to be I, to 24. So I would have changed to 24. Then we said directly change I to 37. Oh, and then we print out I. But if I print, what I meant to do here was actually, in fact, let's print out star P. Yeah, right. So that's interesting. In code like this, there's just no point. Yeah, no use for pointers. I mean, what does it give you? Nothing yet. Pointers really become useful once we mix them with functions in particular. We mix them either with functions or to tie together data structures. But for the sort of code we're writing currently, they only matter with functions. Well, I'll show you in a little while why they matter with functions. Let's see if I've got another lecture slide. Yeah, so that's showing.
Can I make a point really quickly?
A point?
Andrew,
you want to make a point? A point about pointers?
Oh my goodness! Oh my goodness! So the reason I'm saying this is just because I realize that there's a lot going on sometimes, especially with pointers. And when we introduce memory, there are actually 3 things which we're introducing all at once, some of which are confusingly similar in terms of their notation. And so I think it can sometimes be useful, if you don't mind, just going through really quickly, like what are the 3 things that we are showing you, just so that you can kind of try and identify them. So the first thing that we showed you is that pointer type. So instead of you saying int I, like we've got on this slide, we've got int star or int asterisk. And that's talking about, instead of it storing a number just by itself, it's storing a place in memory. The second thing that you then saw was that ampersand I, which we've already seen in printf, but we're using it again in a slightly different way. And that means given some variable, so some integer or some double, ampersand tells you where you can find it. The last thing that we'll see as well is we're seeing using star before the name of a pointer, and that's what we call dereference. And that's basically, given some place in memory, tell me what the value is there. So those 3 things, whenever you see like a star or an ampersand in the context of pointers, it's pretty much always going to be one of those 3 things. And if you can identify which of those 3 things it is, that'll go a long way towards helping you understand what's going on. And so even for the rest of this course, one of the things that you'll be doing basically is looking at those 3 things and trying to understand, is this dereferencing, so going from a pointer to a value? Is this an ampersand, which is going from a variable to a pointer? Or is this creating a pointer, which would be like int star or double star?
Yeah, good summary, Tom. I would say, yeah, one thing that worries me in understanding all of this is how much particular symbols, particular characters get used for. So asterisk is our way of writing multiplication, so we've seen that. but it also gets used as part of a pointer type. So we say int asterisk to mean pointer to int. So it's used as a part of the type notation. So that's a second use. But wait, here's a third different use. It's saying, oh, given a pointer, I want to talk about what it points to. Dereference. Use the pointer to get at what the pointer points out, and either get its value or assign to it. Yeah, lot to get your head around. Alright, you'll see us use a special hash defined value for a pointer that points at nothing. It's very useful, not yet, but it will be later on. Not yet, we don't really need it yet. You might see it, but we don't need it yet. To say this pointer points at nothing. Not that we haven't given this pointer a value, but it points at nothing. So it's a special pointer value that points at nothing. We'll use hash define null. This is a complicated thing which very few C programmers really understand properly, so don't worry. I'm not going to try and explain it properly to you either. But it's related to 0, so it's but for now just assume it's null. If you print out a pointer containing null, you'll see zeros. Alright. Oh, so we've done all of that. All right, we're ahead of that slide. Pointers and functions. All right, this is how C functions work. Yeah, as you get you'll find people like me who've seen, I've lost count of how many computer languages I've seen, will use general terms to describe things about languages, because we've seen 3 languages that do this and 4 languages that do that. So when we see a new language, we'll say, it does functions, variables are passed by value. So which is not very helpful to you learning your first computer language, but C function variables are passed by value. What that means is a function is only given a copy of whatever is in the variable, and it can't change the variable back in main. So a function is given a copy of a variable. Let me show you this in operation. Let's go back here. Let's change our name to be increment.c while I think about it. Alright. Let's suppose I wanted to write a function to add 1 to a variable. So I want a function and I want it to print out 457 after this is run. So increment, it's an English word for add 1. Why didn't you call it add 1? Alright, I'll call it add 1. Alright, so we have to give it type. It doesn't return anything, and it takes an int variable, and I'll call it x. So we'll tell the C compiler about the function I'm going to write. You don't actually have to do it in that order if you're writing. Often coders write the function, and when they've figured it out, go back up and put the prototype at the top. Alright. Oh, it's pretty easy. X++ return. All right. This is a sort of a weirdish function. It doesn't give us an output back. So we have this special word for void. This really means the empty set. To say we're not passing back any output. Our job is, given a variable, add 1 to it. We'll try compiling this. That program doesn't work, and I think DCC is actually smart enough to spot it doesn't work. But let's see. that's by the way a good day. You often see students complaining, "Oh, the compiler doesn't like my program." If a compiler can figure out your program's wrong, that's so great. It's telling you, it says, go and fix line 37, Andrew. That's easy. It's when your program is a valid C program, but it doesn't do what you want. That's hard. Oh, I was wrong though. DCC isn't smart enough to tell me. That's interesting. Yeah, that's it. You could puzzle your tutor with that one. Should a compiler producing an error message for that function? That's an interesting question. All right, I run this. Oh, all right, because I haven't saved it. I'm an idiot. Let me try again. Maybe DCC will. No, it does even after saving. All right, let's start again. Oh. All right, it hasn't incremented the variable. Why? All right. I've said before, that looks like a variable declaration. And the reason for that is it is a variable declaration. So those variables there in a function are special variables because they get initialized with whatever is passed as that argument, as that input to the function. So this function only has one input, so x is a variable, it's an int variable, and it gets initialized with whatever argument, whatever input is given to the function, and in this case that's 456. So x will be initialized with 456, x will be incremented, 1 will be added to it, sure, but then the function returns. Now x exists only here in these braces, so that's the end of it. This was a waste of time. Adding 1 to a variable and then never doing anything with it, it's a waste of time. So that's why I thought the compiler might warn me. I back here in the main function is unchanged, so that prints out 456. And this is the thing. We've got a copy of the value passed to the function. Changing the variable in the function can't change anything. What can you do about that? Well, let me show you. And I think, well, you obviously have a good idea. Let me rename that, add one broken, and write a different add one function. And what I'm going to pass in is a pointer. Well, I can call it P. Fix my clumsy. I've got the caps lock on. Oh, there we go. Star P plus 1. Yeah, there's an interesting point there that we have to mention. And we'll pass into add 1 a pointer to I. So we've got a different type for add 1, a very different type. It looks almost exactly the same. It takes an int star and add 1 to whatever variable it points at and says call me. So we often talk about a contract with your caller. So that's sort of add one's advice to anyone who wants to use it, saying give me a pointer to an int variable and I'll add 1 to it. Right, so let's try that out. Oh no, no! What the hell does all of that mean? And this is a nice example actually of not panicking. Alright, so this first error, yeah, it doesn't make sense to me. But it's pointing at this bit here also. And also maybe it doesn't make sense to me. But I get down to here. Conflicting types for add 1. This is DCC saying, oh look Andrew, here you said this and here you said that. And they don't match. The big thing it's worried about is int star and you said int. You've said add 1 takes a pointer to an int up there. Let me fix that. Update that. Let's try that out. And it has actually managed to add 1 to I. I'll write this in a slightly different form. I've written it perhaps in a compact form. I could have done it in multiple steps. I could have declared a pointer variable, say z up here, made it z point to ampersand I, and done this. And that will have the same effect. That will also increment I. .457. There we go. That's probably a better way of putting it. It makes it absolutely clear. How did that work? Why does that make a difference? Well, remember, a pointer contains the address of the variable, where to find the variable. So this value gets passed through, and then we use it inside the function. So it doesn't matter, we've got a copy of the value, a copy of the address, that's still just as fine. We can still use it there and there to change the variable. Change any int variable. So this is why we've come to pointers today, is they give you a way to have a function change a variable. I've got one more slide to show you and then we'll have a break. I've got a nice diagram. No, I don't. It's the wrong diagram. Well, that's terrible. Alright, I'll fix that up and come back after the break. Alright, so we'll come back to that after the break, but let's take a 5-minute break and start again at 10 past the hour. Alright, back we are. So this is where we left off. This was the sort of a diagram of the impasse we had. This is why we could make that function work. So main calls the function, gives it a copy of a pointer to the variable. So we're passed a copy of the pointer to the variable, but we can still use that to get back to the variable because it's got the original address of the variable. It's a huge difference. It's a fundamental thing in computing. All right, and that's what we just did. We'll come back to that function. Oh, arrays. All right. Let's see something with arrays. Yeah, arrays are interesting. Arrays and pointers, arrays and functions. We'll be walking backwards and forwards over them. But let me show you an implication of all of this. Wait. Oh, there we go. Huh. All right. Let's do an example with an array. We'll call an array that. We'll print out what the address of the first array element is. There. I'm going to call a function, just a regular function. I'll make this a typical little program. We'll define the size of our array. Hash define size 50, say. We'll have a function f, which we pass the array to, just to see what happens. Junk that dead code, junk that misleading comment. Right, so there we're set up with a little C program, and the last thing I want to do is, after I've passed the array in, to see what's happened. Have I got everything right here? Will that compile? Oh, so close. That's B. Oh, we haven't called the function though. Let me call the function. Pass in A. We're going to see both those values are the same. Now, yeah, I don't really want to. I'll come back to this, but there's a complicated relationship between arrays and pointers. The end result is, if I go to pass an array into a function, what's passed through is really a pointer to the first array element. So we'll see here, we say, oh, give me a pointer to the first element of A, and that pinch out is this magic value. We pass A through to the function f, and look at where it's argument B, and we say, oh, give me a pointer to the first element of array B, and we see the same magic value, the same address. So they're the same array. Alright, We'll come back to that, but that's your introduction to that. The effect of that is, if I change an array in a function, change an array element in a function, it changes the array element outside the function. So this will change an element of the array A. I'll show it to you. We've got another thing we want to do, so let me just show you that and wrap this up. Let's initialize this array too. Let's put zeros in this array. And make that correct. So close. Run it. So we're going to revisit this and talk about this in later lectures. But yeah, arrays and functions have a complicated similarity with pointers and functions. Oh, let's get my lecture slides. Oh, you can have pointers to pointers. You can have fun with that, but not for weeks to come. Alright, let's move on to a topic. I'd like to continue our theme of using games as examples to practice our coding. Let's write a program we can use to shuffle a sort of a virtual pack of cards. Though instead of cards, we'll just have numbers. So we're going to write a program that will take some numbers as input, shuffle around them in order, and print them out again. And we'll do it using pointers. So let's see how we might do that. Yeah, I'm not sure we'll get through it in the time we have left, so we might have be prepared for there to be a cliffhanger at the end of this lecture. Alright, so the program is going to read in some numbers, change their order and write them back out, like shuffling a deck of cards but with numbers. As an example. Alright, I'm going to call this shuffler. .c. Alright. So yeah, well, let's think about what we might do. We have to store these, so we might have, I guess, a deck. We'll store. We've got numbered cards. We'll call it. So we'll call the array cards. Oh, we've got into delete mode accidentally. How big? We don't. Yeah, it's a good point. We probably want the user to be able to say how many cards they want to shuffle. So, but we've still got to have a size for an array. It's a common dilemma in programming. The user's going to enter a number 5, 10, 50, but we don't know what that number is. But we've got to size our array. There are a few ways to do that. There's some cleverer ways to do this which we can get to later. But for now, we're just going to say predefine it. Say, yep, the biggest number of cards you can enter is 1024. Now what do we do? It can be often useful to think of this in functions. We might write a function to read the cards. which takes, well, what are you want to take? Deck of cards, and it's of size max cards. We might write a similar function to say print the cards. Now, a bit more complicated because we need to know how many cards the user decided. So when it reads in cards, well, I guess we'll let the user say how many cards they want to read in. When we print them, we'll have to print it out however many they read in. And I guess we might have a shuffle cards function as well. So we might do this program in terms of 3 functions. Now, I won't say this is easy, but it's a skill you've got to work on faced with a problem like this. Not tomorrow, not maybe next week, but by the end of COMP1511, I want you to start thinking like this. Faced with a problem like this, think, oh, I got to write functions to do A, B, C, and if I've done that, I can put them all together, and I've got a function. I've got a program to do what I want. So I've sort of sketched out here the functions I might write to solve this. All right, so let's start on one of them. This one. Read cards. Reading in all the cards. And we know how. I think we know how to do a lot of this. So something like we print out a message saying how many cards. Asking how I want to read in. And then read that number in. And look there. We now know what we're doing. When we say ampersand cards, we're giving scanf a pointer to this variable, an int star which points to this variable, and that lets scanf change this variable. Now what? Let me put together some code. All-time popular variable is I, loved by so many programmers. We need a loop that executes through I think I have a design problem, but let's see if my program compiles. Yeah, I think it's pretty common for you to make mistakes like I've made, not even thinking about it. Let's see if what I've got works. There's a few things I'm worried about. A few things. I'm not checking whether the scanf manages to read something. And a lot of examples we do, we get a bit lazy about that. It complicates and gets away from the main point we're trying to make. So I won't bother with that for now. And there's also, I'm not checking about, is this variable sensible? Could they enter a negative number? Yeah, it'd be smart to check that as well. So, but we'll also not bother with that for now. Let's just see if what we got compiles. Called it shuffler.c. Let's spell DCC properly. Ah, all right. That's interesting, isn't it? I can say I've told DCC, this is I might have a function called this, and I might have a function called that. I didn't actually have them in the end, and DCC didn't worry about that. If I'd actually used them and hadn't defined them, DCC would have been very unhappy. But because I don't call these non-existent functions, it says, it just keeps on going. It's not something you probably should do in general, but it's handy when we're halfway through writing a program. We can say, I'm going to have a function called this, and I haven't written it, and I haven't called it. The other trick programmers use a lot is they just write a little bit of a function. A stub is what we'd say of a function, and come back later and fill it in. Alright, does this work? Does this read in numbers? How many cards? 5. And they are 45, 56, 78, 89, and 2. And that was accidental, sorry. It would have been smarter if I'd written the loop and looked at the loop and thought, does this loop look right? And then added the scanf. It's not a bad idea to do your whole loop and then fill in the guts, the body of the loop. Make sure you've got a loop that goes over the right numbers. Maybe just put a printf in there to see it's doing the right thing, and then put what the work you really want the loop to do in there. And then you avoid looking like me, making embarrassed about making a mistake like that. Writing a loop that never ever would have terminated because you forgot to increment the variable. Let's try it again. Or can I cut and paste? Will VLab let me cut and paste? Oh yes, it does. But that won't help because I haven't recompiled. It's time for sort sure. So it read 5 numbers. Did it do the right thing with them? Yeah, at this point we sort of need some output. So many programs take this form. Oh, I'll write the code in so many languages. Oh look, I'll write the code to get stuff in. Well, does it work? I'll better write some code to put the stuff out. That appears just everywhere in programming one way or another. Print card. So it's got to take the cards and how many cards there are. Alright. Let's get, and print card is here. Alright, there we go. And this loop's easy. So that's just write out the elements, write out element 0, 1, 2, 3 up to length. 0, 1, 2, 3 to length minus 1 of that array. Hopefully that's sort of, you're sort of looking at that and thinking, oh, I think I know how to do that. Hopefully. So I'll just snarf that loop from the other function. I'll use a different variable. I recommend you, as I said, I recommend you use different variables until you got a bit more used to functions being their own little world, just so you don't get confused in your own head. The C compiler won't get confused. Alright, printf that, and I'm going to write them on one line. I like writing numbers on one line. So that prints out each number with a space after it, then writes a new line. Great little function there. There's a slash there. Let me clear my scribbling there. And that all looks good. Oh. Alright, we've got an error here. That should be length. That's fine. Let's fix that. That's the name of the parameter we've passed in, length. We're meant to write. See, that would have been, that's why putting a comment here is so useful. Write out the first length. If I'd written out that comment, I actually would have spotted that straight away in my program. Good sort of coding habit. I've still got a problem here. A bad problem. Oh, and there's a superfluous ampersand there. Printf doesn't get past a pointer to the variable. It can just do with the value. It just wants to print out whatever in deck J. You could write a printf that did that and wanted a pointer. That would be possible, but it's overkill. You don't need it. It would make printf painful to use, actually. But all right. Apparently, I haven't saved. I'm going to be left with one error. And here's my problem. There. N cards. Where have I told the C compiler what it is? Well, I haven't, because what I really want is whatever was scanf'd here. Way down, I called read cards. It did a scanf and worked out how many cards the user wanted to enter. I now need to pass that to print cards to tell it how many cards to print out. How do I do that? And there's no way. Now there are two possibilities here. It's tempting, by the way, if you've just seen pointers, to think, I'll do this with a pointer, and you could do it with a pointer. So we could pass a pointer through to read cards and get me a value back. But if you just need one value back from a function, the best way is to make it the output from the function, make it what the function returns, to change the type of read cards. And so I really should say what a comment. Get it clear in my head. Read that many cards into deck. There we go. All right. So that's a better design for the function. Have it return an int, which is how many cards. So I'll have to change my function to say return n cards. So it makes my function do two things. It's a bit tricky. It's not ideal, but it changes the array deck and it returns how many cards it read in to the array deck. And then I'm going to have to change up here where we give the C compiler warning, the prototype of the function to come, to say it's that. And now I can say, call it deck size. We could call it n cards, but as I said, it's not a bad idea to use different variable names. Well, it sort of is and isn't. If you're a proficient C programmer, that might confuse. If you're a proficient C programmer who's expecting code written by an expert C programmer, they might get a bit confused and thinking, why do they keep changing that variable name? They could just call it the same thing in every function. But when you're taking your first steps with functions, it's nice to have different names in every function, even though you can reuse the same name within functions, between functions rather. Okay. Is that correct code? Print card. Print card. So, time for sure. All right, let's try that. How many cards? One card. 45. Oh, look at that. It's brave. 3 cards. 56, 789, and 23. Oh, lovely. All right. Now notice what I'm doing. Notice that I'm writing a function and then testing it out. The world is, if you can test out a single function in isolation, you can write a function and test it out without writing more code. The world is so much a better place for you. Life is so much easier. We go to great lengths to be able to set this up in our programs, to be able to test functions in isolation, because it just tames the complexity of coding. if we can write 10 lines in our 1,000-line program and just look at those 10 lines, test those 10 lines, confirm those 10 lines are working without worrying about the other 990 lines in our 1,000-line program. So we've written this function, and it seems to work. There's weaknesses. The code often has weaknesses, so we're worried about what happens if this scanf didn't manage to read something, what happens if this scanf didn't mean to read something, and we're worried about what about other values for end cards. So we're going to come back to those, but let's race on, knowing that our code, this might have to be improved. So we're worried about this code here. It's brittle, it's uncertain, but let's fill in some other parts. It's not so when we're trying to just walk through concepts, that's a good way to do things. It's not necessarily a good way to do things in general as a coder and as a professional coder. We talked about the style. It's a very bad habit to scroll out your ugly code and think when it's all done I'll come and I'll pretty it up, I'll make it readable, I'll make it maintainable. You want to be cleaning up, writing good code as you go, and in general you want to be writing solid, robust code as you go. But so excuse me for not doing that. I'm left at my last function. Well, perhaps my second last function. We may still need a function here. So let's copy it in there. Shuffle cards. We'll take the deck and the deck size and change it. Actually, I'll show you doing a stub function. That's not a bad idea. Where we put it? Oh, we might as well put it up here. Try and have your functions in a logical order, generally going from most important to least important, but logical order. So it's void shuffle cards. Oh, that's what we wanted. Instead of doing something useful, we'll just write out a message in here. Not a bad thing to do because we can see everything compiles. And so make sure how we're doing there. Oh, look, I've got a mistake. Print. Oh, I've got a mistake up here. Oh, shuffle cards. It should be the cards there, shouldn't it? That's the name we're calling the array there. We've got it compiling. It's not shuffling because the body of the shuffle function is just a stupid message. We try it out. Hit a 3 and the cards are 1, 2, 3. And it prints out. Yeah. Alright. So a professional programmer might put in shuffle cards unimplemented. Something like that. Alright. But let's implement it. I had a shuffling plan. I had a clever idea before that I was going to try and do, which was with swaps. Some people when shuffling do swaps. By the way, there are many bad ways to shuffle cards. If you're playing cards with people, be incredibly aware that there are many ways to cheat when shuffling cards. There are a few good shuffles. Famously, the American General Eisenhower in World War II got a professional magician to distribute to his troops, the millions of Allied troops in Europe, how to shuffle cards because he was worried about his troops being cheated by those European people that were liberated. Fun fact for today. Alright, let's see how we're going to shuffle the cards. I had this idea, this weird idea. Well, I'll do it by going through and swapping pairs, sort of randomish pairs in the deck. So I'll do that with this one, a swap function that swaps those two values. Yeah, we haven't done a swap nums function. We'll come to that shortly. And I got an idea. Well, it's a good idea to try this out, isn't it? Now here's my idea: is that we'll get J by taking I times 3% length. All right. What possible values can J have? Well, what possible values can I have with this loop? I can be 0, and then when does I? Oh my God, I doesn't change. Some people don't learn. So that shows you this idea of start to think logically about your loop. So I've looked at that function and said, what values can I take? And see, I is only ever 0. Now what values can I take? I can be 0, 1, 2, up to length minus 1. Can I be length? No, because this would be false. So the loop won't execute with I having the value length. What values can J be? 3 times I percent mod or modulo length. So J will also be a valid array index. It will be 0 to length minus 1. So that this should give me valid array index, but I don't want to chance that, and I haven't written this function anyway. So I'm going to, instead of calling that function, I'm going to print it out and see what it does. It's a good example. I'll see if this generates sort of an interesting card swaps and might be working for me. So it's swapping I and J. So we'll just see what it would do, and then we'll try and write the swap functions and see if we can get it working. We're very close to running out of time, but let's see how close we get. Compiled. We'll enter 5 cards. We'll enter 1, 2, 3, 4, 5. Oh, that's a bit sad. Swap card 0 and 0, 1 and 3, 2 and 1, 3 and 4, 4 and 2. Yeah, that's sort of interesting. That would rearrange things as well. It's a bit sad for card 0, but yeah, that looks nice. Alright, so we just need a swap nums function. Alright, I can do that. Well, let's do it up here. A type void swap nums. And it's going to take 2 pointers. Int star p and int star q. And let's fill that last one in. Okay, let's put a comment here to say what it does. Alright, I'm on this. This is easy. Alright, I think I'm there. We'll leave that printf in there for now. Well, actually, no, we'll comment it out. Alright, today's life tip. It's really common when you're programming to say, no more bugs in my program. I'll just delete all that helpful debugging statements I had, all those helpful printfs I added just to help me debug my program, give me extra information about what's in this variable at that time. But my program has no bugs, so I'll just delete it. 5 minutes later, future you discovers, oh, there's another bug. Wait, I need that printf back. So if you just turn it into a comment, you can get it back very easily. There are even cleverer things you can do in that line, but that's a lot better than nothing. So let's try it out. 5 cards, and we'll enter 4, 5, 6, 7, and 8. Huh. That's a bit weird. Let's try that again. That's strange. Oh, sorry. We'll just try with 2 cards. Often it's good to just try a really simple input when debugging. So rather than trying a realistic input, you know, maybe we're going to be shuffling 50 cards, 52 cards. Just try shuffling 2 cards and see what happens. And we'll put 67 and 78 in there. Oh, that's okay. Alright. Let's try. Didn't move them, but alright, we'll put 4, 5, 6 in the cards. Oh. All the cards became 4. Let's now uncomment our printf there, and so we can see what swaps are being made. And maybe that will give us some clues. 3 cards. 4, 5, 6. Oh, so that was the swaps that were tried. Alright. Let me show you another debugging trick. Sometimes if you've got a function like this, it can be helpful to use it for debugging. So we often write output functions just to use in debugging. So let's grab this one and use it up here maybe. Oops. So we'll use it to print out the deck like this, and length. Looks nice. Oh, we don't need the max cards bit. There. So this will let us see what's happening to the array with each swap. Maybe that'll help us understand our bug. I can see some people in the chat have spotted the bug, but yeah, and that's great. You can see the bug straight away, solve the bug, that's great. But we also need to have tools, ways, you know, of attacking bugs that we can't see instantly, because sooner or later you're going to face a bug you can't just look at your code and spot. So 3 cards, which are 7. Oh, we'll stay with 4, 5, or 6 just for simplicity. Okay, we swapped 0 and 0, and that did nothing. Not a surprise. Then we swapped 1 and 0, and both of them became 4. And we swapped 2 and 0, and then that one became 4. So it's our swap function. Our swap function's broken, as some of you have spotted in the chat. Why would that be? Well, look at the swap function. That says make the contents of whichever variable p points to the same as q. The same contain whatever the variable q does. So both those variables now contain the same thing. Then we say put back in the variable p whatever's in the variable q. So we're only left with, we need to have another value here.
There's an analogy that I've heard used to describe this that I might be spoiling some tutors, but I think it is quite helpful. If you imagine that you had in front of you a glass of milk and a glass of water, and you were trying to swap which cup had the milk and which cup had the water, what we're trying to do at the moment is pour the milk into the water and then try and pour the watery milk back out, which isn't going to make sense. So the only way that you're able to do this is if you imagine that you had a third cup. Well, then you can pour the milk into the third cup. You can put the water into where the milk was, and you can pour the third cup back into where the water was.
Do I really need a third cup though?
Ooh. Well, as far as the metaphor goes, perhaps. It's an interesting thing.
So, to do it in a sensible, simple way, you need a third glass to do this rearranging. Yeah, so it's a good metaphor. But there are weird things you can do to get away from that in computing. Actually, I think you could do it with milk and water too, given certain physics or things like this. Or maybe a filter. Yeah. So if I had a filter that passed only water, I could do it with only. Maybe.
I feel like most analogies, you can push it to its breaking point, but in terms of just hold your drink in the mouth.
So maybe you can tell that I think analogy is the weakest form of argument, but it's actually an incredibly useful form of explanation, which is why tutors who are not stupid use it. All right. I think. Oh no, I've almost got it. Almost. So here's my third glass, if you like, my third place. I save whatever values in the variable that q points to. I change whatever variable q points to be to have the same value as whatever variable p points to, and then I put in p, the variable that p points to, the original value that was in q. And that I'm hoping will give me a correct program. Let's be brave. I'm going to comment out my printf up there that's only there for debugging, and my print cards which is only there for debugging. And I'm hoping we're going to see it shuffle the deck of cards. We've only got a few minutes left, so pressure's on here. 3 cards. All right. 4, 5, 6. Shuffle this. Oh, look at that. That's amazing. 6, 4, 5. All right. Let's try something more complicated. 10 cards. And we'll put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in. And give them back to reordered. That's wonderful. All right. 20. We're going to be brave. Let's see if it hands a 20. Oh, put 11 in twice. Not that it matters. Well, it's a bit harder to spot if it does something silly. Oh, looks like a perfectly good shuffle. All right, so I should warn you again. There are places where shuffling becomes incredibly important. I mentioned Eisenhower was worried about the Allied troops in World War II in Europe being cheated by, I guess, I don't know who expected they were playing cards with, maybe each other. So shuffling, if you're betting money in cards, shuffling's important. There are other places where it becomes used, where you do things for cryptography and related areas. It becomes important, and this is not a robust shuffle in that sense. It's a beautiful example of something we can code up just using simple tools we've learned in the first weeks of C. But there's a whole world of things you could do here to what I'd say is permute these numbers. But this is actually quite pretty. This really simple idea here produces. For a game, for example, might be quite useful. So that's lovely. Beautiful. All right. I did want to come back to this at least a little. There's a big thing here. I'm worried about this. I said your life will be happier if every time you use an array index, you think about how you know this is within the array. So if an array has n things, how do I know this number is 0 to n minus 1? How do I know I is between 0 and max cards minus 1? Do we know that? We don't. Because because I goes from 0 to n cards. What n cards? It's a value we just got from the user here. So the user could enter in 10,000, they could enter 1,000,000, and we overflow this array. And all sorts of bad things can follow from that. And one big thing is security holes that we see again and again. What are you going to do about it? Let's see. I have an idea. If n cards greater than max cards, I've got a problem here. If I wanted to stop the program, we don't know how to stop the program in read cards. We know how to go back to main, but how do we stop the program? That's a bit tricky. But what I can do is print a message saying restricting. Oh. There we go. Just put out a message saying max cards, and then I'll force the value back down into a valid range. So there's a design decision here about what we do. And another very valid design choice would be just stop the program. A third possibility would be to force the user to give me a valid value, so to put it in a loop. Now that's a separate problem. I'm going with a simple thing, and that's stopped me generating a value. Now I know that I can't be too big. Is that my only problem there? What about a negative value? And what about this scanf failing? And what about that scanf failing? So there are other checks we could add there, but no, that's an important one there for us. And that's all we have time for today. So unless there's a good question from the chat that Tom thinks I should cover, I can see the other Tom has been frantically answering questions, but unless Tom, the other Tom number 1 thinks there's a question.
I don't think there's anything in there that's particularly question worthy that Tom hasn't already covered. Doesn't look like it to me.
All right, thank you both Toms for your help covering this. Oh, a big shout out to Shrey, by the way, who I see has been patiently answering questions in the forum. All right, please try to make Shrey's life easy. He's a busy person. He wants to help you as much as possible. Try to tell him as much as possible about your problem. So give him all the information. He's a smart person, but give him all the relevant information you can about your problem, and he'll try to. It makes it so much. This is such a general thing with getting help from people, but in this instance, tell Shrey whatever you can about your problem. Cut and paste best. Screenshots are a bit painful, but worse than nothing. Give him all the help you can when asking questions in the forum. All right.
And on that point, it's useful to note. If you do that, if you do give, Shrey or anybody who's on the forum all that information, it does actually mean that we'll be able to, you might be able to solve the problem yourself. If you have thought through it, and if you've written up a solution, you said, oh, I've tried this, that, and the other thing, and then you realize to yourself, oh, I haven't tried this fourth thing, and then you do it, you'll find that typing out to Shrey or to your friendly rubber ducky, if you've got one nearby, can be incredibly useful.
Yes. All right. Thank you all. So I'll talk to you all again on Tuesday. Get started on the assignment. Yeah, definitely get started on the assignment. Don't expect to get too far, but yeah, get started on the assignment. All right. I'll see you all then.